So in this set of lectures, what we're going to be viewing is molecular orbital theory, how it relates to pericyclics. We'll talk about the Woodward-Hoffman rules, where we have species that are symmetry allowed and sort of contrasted with species that are disallowed. We should realize by now with Foucault's approach, we only consider the frontier molecular orbitals of our conjugated systems. So i.e. the highest occupied molecular orbitals and the lowest unoccupied molecular orbitals. Before we move on, why don't you have a look at this and try to remember exactly where the luma is. And maybe I should have asked you where the luma is in ground state, but of course it's already here, So go ahead and try to answer that, and then we can push on. The luma, of course, is psi3, and psi3, if you notice, has 1, 2 nodes. This is a ground state 1,3-butadiene. Question: what would the HOMO be for the excited state of 1,3-butadiene? So here's a molecular orbital description of cycloadditions. Realize that with cycloadditions, we have donation of electron density from one reactant to the other. And in this case, in most of the ones that we'll be looking at, we want the HOMO of the reactant donating electrons to the LUMO of the other reactant. This is cycloaddition, or this is a requirement of the molecular orbitals in cycloaddition. So let's look quickly at the Diazolda. Remind yourself that the Diazolda is a 4 pi, 2 pi system. You can see we have 4 pi electrons here and 2 pi electrons here in the ethylene, i.e. the molecule representing your dienophile, or the molecular orbitals representing your dienophile. Remind ourselves exactly what this Diazolda is. We have 4 pi plus the 2 pi. So we're looking at ground state species. So we're looking at ground state conjugated diene, and with ground state ethylene. Look closely, because now what you notice is that we stated that it's the highest occupied molecular orbital donating electrons to the lowest unoccupied molecular orbital. And of course the symmetry has to be the same, has to be symmetry allowed. Look carefully, because if you note, the HOMO of the diene psi2 is an asymmetrical molecular orbital. Can you see? Why? Both ends are opposing flavor. Blue, red, and here on this side, red, blue. So we're only concerned with the end. We're not concerned with what's going on in here. Here you can see also there's a blue, red on that side, and at this end, red, blue. So both of these molecular orbitals are asymmetric. So that's an asymmetric molecular orbital, and this is an asymmetric molecular orbital. And so once the click happens, or for the click to happen, therefore we have this symmetry alignment. And so you can see the donation here. Realize that this is called a superficial addition, because in the ground state we did nothing except let the click happen, because the symmetries aligned, with symmetry allowed. However, if they're not allowed, then of course we have so-called antiartificial cycloaddition, and we have to have enough flexibility in that molecule for a twisting to occur, so that there is compatibility, because right now there's no compatibility, but if I twist, there's compatibility. Okay, here you can see exactly why the stereochemistry that results when we have this cycloaddition, in this case Diazolda, occurs. So here we have a molecule, we can see that it is E, and here also we have E. And we stated when we had EE, then of course, both of these groups will be on the same side of the cyclohexene ring. You can see that. Why? Now you note, because you can see, the click happened on that face. Also realize that when it happens, therefore, the ring forms, these guys are going to be on the same side. But another feature I want you to see, is the feature where it's a feature where you realize an S-cis conformation of your diene. Look closely. There's an S-cis conformation, because if you had an S trans, then that wouldn't work. But with the S-cis, now you can see that these orbitals will now align. Very convenient. You can see here we're telling the reader that it is a thermal environment, it's a thermal event, i.e. ground state. Just like the 4 pi 2 pi, which is a thermal event, we can also have cycloaddition, which is photochemical. Here we're looking at the 2 pi 2 pi. What exactly is it? You can see that we have 2 moles of alkene combining together to give you a ring. By the way, you can see immediately what exactly occurred. You have 2 degrees of unsaturation on the left, and now you have just a cyclobutane ring, which is 1 degree of unsaturation on the right, hence a cycloaddition. You also note that we place an H null, Planck's constant, speed of light, so that's a photon of energy, and we're telling the reader that this is photochemically driven. So if you think about the ground state ethylene, reacting with another ground state ethylene, then of course you can see that this is not allowed. Why? Because at the end of it, let's go back here for a second. You can see that this is the hormone of ground state ethylene. You can see that it is symmetrical. And this is the LUMO of ground state ethylene. Why? So one ethylene molecule reacting with other, that's asymmetrical. So this event will not occur. Asymmetrical to a symmetrical click will not occur. But what we can do is if we excite, use imagination, but if we excite one of the ethylene molecules, right, with a bit of light, then imagine we have an excited state ethylene which has a HOMO, yeah, which is asymmetrical, and now that can donate to a LUMO that is asymmetrical. So it's an excited state molecule with a ground state molecule. In the dissolved of the 4pi 2pi, what you had was both molecules were ground state. Here we have one molecule that is in an excited state reacting with another molecule which is in the ground state. So here we have an example of a cycloaddition. You can see here it's a 2pi 2pi cycloaddition because you can see that we have light being involved. Work on that and then we'll talk about it when we're in discussion sessions. Yeah, so to summarize the photochemical situations, you can see that both the 2pi 2pi here, the thermal is disallowed. Yeah, can you see that? Yeah, that's okay, but that's not okay. Yeah, and the 4pi 4pi, the same thing. That's not okay. But on excitation, yeah, the HOMO of the diene will react with the ground state LUMO of the diene. And the same thing here. The HOMO of the excited state ethylene reacts with the LUMO of ground state ethylene. Ah, this is interesting. This is the carbene. In organic 1, we knew that the carbene donates an electron and at the same time, yeah, will accept an electron, a pair of electron. Accept a pair of electron and you form this cyclopropane, like in the Simon-Smith, for example. Well, what I want to show you right now is it is a cycloaddition because you start off with this carbene. You can see that the empty p orb is the LUMO, and now you can see that this sp2 hybrid, yeah, is acting as the HOMO of the carbene. This vestigial nipple this nipple that we thought was vestigial back when we did our basic organic chemistries becomes significant later, because now you can see that, yeah, HOMO reacts with LUMO here, symmetry allowed, and here you can see there's a direct symmetry with the HOMO of the carbene with the LUMO of the alkene. Yeah, so we have this sort of synergistic relationship. So yeah, so yeah. So with that, we're going to talk about electrocyclics. The first thing you should note about electrocyclics is in an electrocyclic reaction, it's an intramolecular event. We can push forward from left to right in a ring forming reaction where the ring, yeah, has fewer pi bonds than the reactant, or we can even have the reverse where the ring itself, yeah, breaks down to give you a acyclic system which has a pi bond extra. We'll show you that later on. The interesting thing about electrocyclics, this type of pericyclic, the only thing that matters, the only frontier molecular orbital that matters is the highest occupied molecular orbital. Once we can determine the symmetry of the highest occupied molecular orbital, then everything else will become apparent or become easy to elucidate. So we're going to determine the symmetry, then we're going to look at the rotations of these species, and then, of course, elucidate from those mechanisms the products, whether it's a ring forming or ring opening reaction. You can see immediately that we have here from left to right a ring forming reaction, but here, yeah, in this case we have a ring opening reaction. Note, in the ring forming reaction, we started off with 3 pi bonds in this case. And of course, you can see now we end up with 2 pi bonds and a ring. Still the same number of degrees of unsaturation. In the ring opening reaction, we have a new pi bond, but still, we should realize, ring plus alkene, 2 degrees of unsaturation, 2 pi bonds, 2 degrees of unsaturation. So there's no change in the degree of unsaturation, just in the number of pi bonds. So here we have something quite interesting. We have here a diagram showing you this cyclohexadiene, which has both mu files on the ring, yeah, cis, and of course, once I perform a ring opening, I end up with an E, Z, E, right? And then when I treat it to a photochemical situation, look, the 2 groups are now trans. Now, what exactly is happening? Note, right, that if we treat the species now with in a ferment event, then we have a ring opening, and now we have a EZ, right? Let's just make sure we know this nomenclature before we move on. Note, in the conjugated triene, yeah, that first alkene is of course E. Yeah? See, it's trans around this double bond. The middle alkene is Z, and here this alkene is also an E. So we have a E, Z, E. If you inspect, on closer inspection of this triene, you can see that we have here an E, have here a Z, and here a Z. So it's a E, Z, Z. Remind yourself, yeah, that the E will always come before Z's. Why? Because at the end of the day, alphabetically, yeah, that's how it is. Note, there's one constant. Yeah. There is Z. If the triene does not have a Z here, the event will not happen. That ring closure will not occur. The highest occupied molecular orbital determines the outcome of the electrocyclics. In the case of the butadiene, in the case of the triene, I should say, you can see that the highest occupied molecular orbital is that of psi3. realize that Cy3 is symmetrical. This is ground state triene. The highest occupied molecular orbital is symmetrical. So all of this lot here is vestigial. Really what I need is this guy. Why? The end bits here. Yeah? Symmetrical. Note that we're dealing with, in this case, the molecule where both methyl groups are pointing out from the plane. So literally that alkene here is E, and that alkene here is E. So really this is an EZE triene. This triene, or any electrocyclic, the mechanism is that of a rotation of those ends to form the ring or to open the ring. You can see that if we have a symmetrical molecular orbital, then we'll have to rotate in opposite directions to have ring closure. That's where the overlap occurs. This is disrotatory. If we have an asymmetric molecular orbital, then for the ring closure to occur, i.e. the two colors, these two colors here meeting, then of course you can see that we're moving in the same direction, which is conrotatory. You have to tell the reader what rotation occurs. So here, for example, I'm just asking a simple question. It says, which highest occupied molecular orbital is represented in the following, right? Please go ahead and work on that. We're going to push on. Let's look at our first example. You can see here I have a EZE. If you note, both of these guys are pointing out. Yeah, pointing out, so I call them outies. This of course is standard Z. Alright, so it's a thermal event. So what we need then is if it's a thermal event, why? And we know electrocyclics are homo, so really what we need is ground state triene. It's a thermal event, so we need the homo of ground state triene. The homo of ground state triene, remember, is Cy3. Yes? The rotation, because Cy3 is a symmetrical molecular orbital, then the rotation has to be disrotatory. This is what the picture looks like. You can see that on rotation, both methyl groups are pointing on the same side of the ring. And so this product, yeah, which is a cyclohexadiene, will have both methyls cis. So really what I should have here is the cis cyclopentadiene. Not pentadiene, I should say, hexadiene. Yeah? What about this one? Let's do this in class, but in the discussion session, and we move on from here. This is an interesting question. It says, which of the following, it says, will the following electrocyclic reaction occur while a thermal, photochemical, or yeah, or thermal disrotatory. So thermal con, photochemical con, thermal dis, right? Or both B and C. What we should do then is go over this during our discussion sessions. The one thing I want to point out to you now is this. The highest occupied molecular orbital is the molecular orbital that is responsible for any electrocyclics. Let's even expand upon that. The highest occupied molecular orbital of the acyclic species is the one that is responsible for the electrocyclic. So firstly, what I can do to start, I'm just going to draw this molecular orbital. I don't know which molecular orbital it is, but I know for a fact that it is EZE. Yeah? So it's an outie-outie. The product, or the starting material in this case, is of course the ring. And the ring has two methyl groups on the same side. There's the ring close. That's overlap. So how do I get EE? How do I get an outie? For this to get to here, this position, that's this position here, I have to rotate 90 degrees that way. That would give this bottom one the shaded color, yes? Why? Because we move from here to here. For this to have that assignment, which is the E, i.e. outie, yeah, we have to rotate 90 degrees that way. If I rotate 90 degrees that way, then of course the shading will also be on this side. This is a symmetrical molecular orbital, isn't it? So the question is, which situation or which event would require a triene to have a symmetrical highest occupied molecular orbital? Remind yourself, in the ground state, psi3 is the highest occupied molecular orbital. Is it symmetrical or asymmetrical? And in the excited state, psi4 will be the highest occupied molecular orbital. Is it symmetrical or asymmetrical? With that, you can determine the answer here, because another thing they ask is, what rotation do you have? Are these going in the same direction or in opposite direction? So we'll talk about that during our discussion session. Let's move on. We'll also discuss this one. You can practice this one and bring it to our discussion session next time we meet. Now herein we're going to elucidate our products from the electrocyclic ring opening. Yeah, so in this case here I have a cyclobutene that is cis for both methyls, and so therefore, and on thermal ring opening, yeah, we end up with a 2E4Z. Remind yourself that this is a conjugated diene, and if you note, right, the product, in this case the acyclic species, has to have an S-cis conformation. In this case here, we generated the 2E4Z. So that's the E, and you can see here that this is the Z. So one outie and one pointing inwards. It's a thermal event, so of course the thermal event of the acyclic species, HOMO, which is really HOMO of the ground state diene, yeah, is psi 2. And of course psi 2 is asymmetric, and so it is a conrotatory system. Now let's move on to the photochemical event. In the photochemical event, now here we're looking at a conjugated triene. When you excite, you can see that initially in ground state triene, psi 3, which is symmetrical, is our HOMO, but when you excite in a photochemical event, then of course your HOMO is now psi 4, which is asymmetric. Here, yeah, we're looking at a species which is EZE. So it's an outie-outie. You can see that at the end here, it's asymmetric. And so the rotation that has to work for the ring closing is, of course, conrotatory. So here's the situation. Yeah, in a photochemical event, you can see that this asymmetric system, yeah, for this triene, yeah, is photochemical. Here, for example, yeah, we've gone from the psi 3 to the psi 4 because it's photochemical, and then the rotation becomes conrotatory. Here, for example, you can see that we have a cis arrangement. On thermal ring opening, of course, we end up with the EE. Yeah? And then, of course, we go on, yeah, like that. We can discuss this as well in our session. And then we can work on this one. Maybe this is a problem that we saw before, but if not, we can work on it when we see each other next. In biological systems, of course, because this is where we're heading, right? Most likely biochemistries, medicinal chemistries, pericyclics play a really important role. So, for example, we talk about phototoxicity, where, for example, if you think about it, yeah, if you have systems like this where you have breaking the bond, yeah, and so on, yeah, so damaged bases, yeah, and intra-strand crosslinks, and yeah, that sort of thing, or interstrand crosslinks, then you'll have mutations. Realize this in DNA, why? We can have a 2pi 2pi. It's a photochemical event, and that will create a mutation. That's why it's not recommended to spend too long in the sun, because then you can have mutation and end up with some nasty stuff, yeah? All right? This is also the reason why DNA has thymine, because it is methyl uracil. Uracil does not have this group, yeah? Methyl uracil, yeah, this event is a lot less probable in DNA because of the sterics. In uracil itself, without the methyl, then it's more likely. But a mutation in RNA, i.e. via uracil, is not that important because we produce a copious amount of RNA which we can get rid of quite easily. Here, for example, we also see where the production of provitamin D3 is light driven. So you can see there's a ring opening reaction right here. to give you the conjugated triene. And then, of course, we have another event, a sigmatropic rearrangement, yeah, which is Fermi, yeah, to give us vitamin D3. So it tells you why you need to be out there in the sun to generate vitamin D, yeah, for your general health. We can talk about this in class. Bioluminescence is kind of important too, right? I don't know if you know about, of course you do know about fireflies, etc., etc. And this is exactly how it works, because it is a chemical reaction, yeah? It's a chemical reaction. And the most important bit about bioluminescence is right here, yeah? The chemistries drive us to have this cyclic species in luciferin, yeah, and it drives this cyclic species, and when this cyclic species breaks down, yeah, then of course the energy given off is light. Think about it carefully, yeah. And so that's the end of